In 1990, the United States commanded 37% of global semiconductor production. Japan was the undisputed heavyweight, controlling nearly 45% of the market. Europe held roughly 10%. Nations like Taiwan, South Korea, and China were barely statistical blips on the radar. But in just one decade, the American share plummeted. Today, the United States controls a mere 12% of global production capacity, while Asia controls roughly 75%. One single company, Taiwan Semiconductor Manufacturing Company or TSMC, now commands over 70% of the entire global foundry market and a near total monopoly on the most advanced chips. America did not lose this manufacturing capability to a sudden lack of scientific ingenuity. It was not stolen by foreign spies either. It was surrendered voluntarily. American corporate executives looked at their balance sheets and explicitly chose to trade physical factories for capital efficiency. They pursued specialized design software and outsized profit margins, exporting the heavy, expensive, toxic lifting across the Pacific Ocean. This is the story of how America, the nation that invented the microchip, completely forgot how to build the most critical hardware on the planet. To understand the scale of this surrender, you have to look at what is actually being built. Look at the Apple M3 Max processor. It is a piece of silicon roughly the size of a postage stamp, yet it contains 92 billion individual transistors. That is 92 billion microscopic on-off switches flipping billions of times per second. Building this object requires manipulating matter at the atomic scale. A state-of-the-art semiconductor factory in the 1970s cost $31 million to construct. Today, a leading-edge fabrication plant costs $20 billion. That is a 64,000% increase. It represents the most expensive, complex industrial investment in human history. A single extreme ultraviolet lithography machine from the Dutch company ASML costs upwards of $150 million. It is so massive, it ships in 40 separate freight containers and requires 3 Boeing 747 aircraft to transport. Inside the vacuum of this machine, a high-power laser blasts microscopic droplets of molten tin 50,000 times per second to create plasma. The plasma emits extreme ultraviolet light. The light bounces off the flattest mirrors ever constructed by human hands to project unimaginable architectural blueprints onto photosensitive chemicals. It sets the stage for plasma etchers to carve transistor gates that are so microscopic, the industry had to abandon physical measurements entirely and simply market them as 3-nanometer technology. A single modern TSMC 3-nanometer wafer costs roughly $19,500 to produce. American engineers invented this entire process. Researchers at Bell Labs built the first working individual transistor in 1947. A decade later, engineers figured out how to wire multiple transistors together on a single piece of silicon, creating the first integrated circuits. The United States government actively nurtured this early industry. The Department of Defense funded the basic research and essentially guaranteed market survival by purchasing the very first massive production runs of integrated circuits for the Minuteman II intercontinental ballistic missile guidance systems. Beyond just funding military applications, Washington also ensured this critical new technology wasn't hoarded by a single monopoly. In 1952, Bell Labs held symposia offering transistor licenses to startups for a $25,000 advance. But the real catalyst came in 1956, when aggressive antitrust enforcement by the Department of Justice culminated in a consent decree that forced AT&T to share its transistor patents with the rest of the industry. Companies like Texas Instruments, Fairchild Semiconductor, and Motorola leveraged this domestic policy to build massive, vertically integrated empires. They conceptualized the architectures, built the physical factories, and manufactured the final product entirely on American soil. Silicon Valley mythology sells us a very romantic, sanitized narrative. It credits the computing revolution to brilliant executives tinkering in pristine suburban garages. But this completely ignores the grim reality of the factory floor. The rapid growth of the American semiconductor industry wasn't just built on genius code, it was built on toxic blue-collar labor. From the 1960s to the 1990s, manufacturing computer chips demanded caustic, volatile chemicals. Early facility operators utilized harsh solvents like trichloroethane to degrease silicon, and lethal etchants like hydrofluoric acid to violently strip away layers of oxide. These chemicals exposed the domestic workforce to severe occupational hazards. Injury rates climbed, executives demanded higher yields, and when factory workers complained about the chemical exposure and the brutal hours, Silicon Valley leaders launched aggressive, systematic union-busting campaigns to keep their fragile production yields high and their labor costs low. The environmental toll was also staggering. Cleanrooms generated vast quantities of hazardous waste. Silicon Valley firms buried volatile solvents in underground storage tanks that frequently ruptured, leaking toxic chemicals into the earth and severely contaminating the local groundwater of Santa Clara Valley. A single modern fab can consume 5 million gallons of water a single day. The early physical footprint was brutal. Executives hated the physical reality of chip making. They hated dealing with the unions. They hated the rising tide of environmental regulations in the 1970s. They actively sought offshore alternatives. They looked for jurisdictions with cheaper labor. They sought weaker regulations. They craved an environment where oversight was virtually non-existent. But the actual catalyst for the American manufacturing exodus didn't originate in a boardroom in California, it originated in Tokyo. In the 1980s, Japanese semiconductor firms leveraged massive government subsidies and hyper-efficient manufacturing techniques to achieve unparalleled global dominance. Companies like NEC and Toshiba specialized in the mass production of dynamic random access memory, or DRAM. They crushed foreign competition through sheer unrelenting scale and aggressive pricing. By 1988, Japanese corporations accounted for 51% of all semiconductor sales worldwide. American executives panicked. Domestic memory manufacturers were facing devastating financial losses. So, Silicon Valley leaders did what they always do when the free market stops working in their favor. They lobbied Washington for aggressive protectionism, and Washington delivered an absolute disaster. U.S. Trade Representative Clayton Uter and Japanese Ambassador Nobuo Matsunaga formalized the U.S.-Japan Semiconductor Agreement on September 2, 1986. The treaty established a strict price floor for Japanese DRAM chips in international markets, forbidding them from undercutting American firms. Crucially, it also included a confidential side letter, effectively strong-arming Japan into guaranteeing foreign companies a 20% share of their highly protected domestic market. While the market share mandate eventually helped American firms, the price floor mandate generated an immediate, catastrophic backfire. The policy fundamentally misunderstood the mathematics of silicon fabrication. By artificially forcing Japanese memory producers to raise their prices, the US government accidentally guaranteed those exact Japanese firms massive, legally protected profit margins. Japanese producers earned an estimated $1.2 billion in excess profits on memory sales in 1988 alone. Executives promptly funneled this massive capital windfall directly back into advanced research and next-generation equipment. They cemented their technological superiority using American legislative protection. And meanwhile, the artificial price hike handed a massive competitive disadvantage to American computer manufacturers. Companies building PCs relied heavily on Japanese memory components. Now, they were forced by their own government to pay a massive premium. Furthermore, the treaty completely ignored emerging technological players in Asia. Shielded from the punitive price floors constraining their Japanese rivals, South Korean manufacturers expanded rapidly. South Korean DRAM market share surged from a mere 5% prior to the agreement to an astonishing 40% in 2000. South Korea officially overtook Japan in 1998. The American government had attempted to protect its domestic industry, but it only succeeded in funding Japanese research and crowning South Korea the new king of computer memory. The physical landscape of the 1980s technology sector remained highly segregated. The integrated device manufacturer business model reigned supreme. Companies conceptualized the logic architecture, manufactured the physical wafers, and packaged the final units all under one corporate roof. Establishing a new fabrication plant required tens of millions of dollars early in the decade. Engineers possessing brilliant architectural concepts could not launch independent companies. They needed massive funding to pour concrete, build clean rooms, and purchase advanced lithography equipment. This is where the entire history of the modern world pivots. A man named Morris Chang recognized the inherent massive friction within this vertically integrated system. He realized that the future of computing couldn't be bottlenecked by who could afford to pour concrete. Born in China in 1931, Chang migrated to the United States, earning prestigious engineering degrees from MIT and Stanford. He climbed the corporate hierarchy to become the vice president overseeing the entire global semiconductor business for Texas Instruments. In 1976, he drafted a revolutionary strategic document. He proposed a radical new paradigm, the independent pure-play foundry. Chang envisioned a specialized manufacturing facility that designed absolutely nothing. The facility would focus entirely on fabricating silicon wafers based on blueprints submitted by external clients. Texas Instruments executives ignored the proposal completely. They viewed the concept of manufacturing their competitors' chips as corporate heresy. When the leadership team eventually passed Chang over for the top job, he resigned in 1983. After a brief stint at another tech firm, the Taiwanese government approached him in 1985 with a bold proposition: relocate to Taipei and spearhead the nation's nascent technology sector. He accepted. Taiwan in the 1980s was transitioning from an agrarian economy to heavy manufacturing. The government provided massive land grants and 48% of the initial capital subsidies to ensure Chang succeeded. They bet the future of their entire island on silicon. The Taiwan Semiconductor Manufacturing Company materialized in 1987. Chang served as CEO. He executed the exact independent foundry model rejected by Texas Instruments a decade prior. TSMC aggregated manufacturing volume from dozens of different external clients. This ensured the fabrication lines remained fully loaded and operational at all times. The strategy allowed the Taiwanese firm to ride the relentless mathematics of the learning curve. They optimized yields and dropped per-unit costs far faster than any single American company could ever hope to achieve internally. The pure-play foundry model obliterated the financial barriers restricting the technology ecosystem. Entrepreneurs no longer required $10 million to test the architectural theory. Instead, startups could focus their capital exclusively on hiring brilliant programmers to draft complex logic gates, and then simply transmit the finalized schematics to Taiwan for physical production. And thus, the fabless semiconductor company was born. This dynamic unlocked a tidal wave of innovation across the digital landscape. It democratized hardware creation and it permanently shifted the geopolitical center of gravity toward the east. The old guard of Silicon Valley viewed the fabless revolution with intense disdain. The prevailing corporate culture championed total control over the manufacturing process. Advanced Micro Devices co-founder Jerry Sanders famously ridiculed the emerging horizontal supply chain during a 1994 industry conference. He pounded his fist on the table and proclaimed to the audience, "Real men have fabs." This bravado masked a looming financial apocalypse. The financial burden of maintaining an internal manufacturing facility was multiplying at a terrifying velocity. To maintain the relentless pace of Moore's Law, companies had to continually shrink their transistors, which meant the highly specialized equipment required to print them became exponentially more expensive. The American industry spent $9 billion on new property, plant, and equipment in 1994 alone. Executives dedicated between 15 and 20% of their total sales revenue strictly to capital expenditures. They spent this cash just to keep the production lines running. The economics proved brutal. A facility required an unceasing flow of high-volume product orders to justify the massive depreciation expenses. A fully loaded fab generated profit, but an idle fab generated catastrophic corporate losses. The soaring cost of fabrication eventually overwhelmed even the proudest American titans. AMD bled cash attempting to maintain manufacturing parity with its colossal rival Intel. The immense financial strain forced Sanders' successors to abandon his famous "real men have fabs" maxim entirely. The reality of Wall Street caught up with the bravado. AMD divested its physical manufacturing operations in 2009. They transferred the physical assets to the Advanced Technology Investment Company to create a separate pure-play foundry named Global Foundries. AMD transitioned into a fully fabless entity, and they relied on external partners to survive. Other stalwarts rapidly followed suit. Motorola spun off its semiconductor product sector. It sold crucial fabrication facilities in China to the Semiconductor Manufacturing International Corporation. Giants like Texas Instruments, Freescale, and Infineon adopted a fab-light strategy. They maintained a handful of fully depreciated older facilities for mature legacy products, but they outsourced all of their cutting-edge manufacturing to Taiwan. The massive corporate pivot toward outsourcing aligned perfectly with a fundamental shift in the economic philosophy of the US government. Federal support for the technology sector throughout the mid-20th century had relied on robust industrial policy. The military-industrial complex funded basic research. It explicitly supported the duplication of supply chains to ensure robust domestic employment and secure manufacturing bases inside the country. Washington altered this approach drastically in the 1990s. The government transitioned away from industrial policy and toward a framework known as science policy. Federal agencies like the National Science Foundation directed funding toward academic universities. They stopped subsidizing direct manufacturing capabilities entirely. The new doctrine prioritized the creation of intellectual property. It subsidized software, it funded advanced chemical materials, and it totally abandoned the physical construction of factories. Wall Street analysts cheered the governmental shift. Financial markets relentlessly rewarded companies that adopted the capital light model. Fabless semiconductor companies delivered staggering returns on investments to their shareholders because they were totally relieved of the multi-billion-dollar burden of pouring concrete and buying lithography machines. Management consultants championed extreme efficiency. They advised executives to eliminate redundant capital investments and boost quarterly earnings. But the pursuit of pure financial efficiency triggered a devastating hollowing out of the American engineering workforce. Corporations initiated massive waves of layoffs. They stripped expensive, highly trained labor costs from their balance sheets. Between 2000 and 2010, the broader American manufacturing sector suffered the loss of 5.7 million jobs. The layoffs destroyed vital institutional knowledge. Engineers responsible for troubleshooting complex manufacturing anomalies on the factory floor found themselves displaced. The separation of design and manufacturing erected a black box around the physical fabrication process. When you don't actually build the product, you lose the ability to tinker, to troubleshoot, and to organically discover the next engineering breakthrough on the factory floor. The nation actively traded decades of hard-won physical domain expertise for a short-term spike in corporate valuations. The late 1990s delivered an unprecedented technological catalyst that solidified this shift. As the global economy experienced massive expansion, with the Nasdaq index soaring 86% in 1999 alone, the internet boom generated ferocious demand for highly specialized silicon. Networking giants like Cisco required complex application-specific integrated circuits to route web traffic, while cellular phone manufacturers demanded sophisticated baseband processors. The legacy integrated device manufacturers could not adapt swiftly enough. The architectural rigidity of owning a multi-billion-dollar facility prevented legacy firms from iterating rapidly. They had to keep their factories full of their own products, which stifled their ability to pivot to new technologies. The fabless companies faced no such constraints. Firms like Broadcom, Qualcomm, and NVIDIA pioneered entirely new product categories at lightning speed. Designers utilized advanced software to manage the exponential growth in transistor counts. They passed the finalized blueprints to Asian foundries for rapid execution. NVIDIA designed the graphics processing units, TSMC built them. Apple designed the smartphone processors, TSMC built them. Qualcomm designed the modems, TSMC built them. Foundries refined their internal cost structures. They offered lucrative volume pricing to fabless clients who reserved significant manufacturing capacity. The nimble, capital-light design firms completely crushed their vertically integrated predecessors in the race to supply the digital infrastructure of the 21st century. On paper, the United States orchestrated a brilliant financial victory in the 1990s and 2000s. American corporations dominated the lucrative software and design segments, capturing extraordinary wealth and establishing total monopolies over global digital ecosystems. Apple, Google, Microsoft, and Amazon reached multi-trillion-dollar valuations, but it was an illusion. By cutting costs and abandoning the physical realities of the factory floor, the nation engineered a fragile, terrifying geopolitical vulnerability. In 2021, the bill finally came due. Auto executives panicked during the pandemic and canceled their chip orders, losing their spot in line to tech giants. The mistake cost the industry $210 billion and left thousands of trucks paralyzed in empty lots. Furthermore, because cars use cheap, low-margin silicon, Asian foundries had absolutely no incentive to halt smartphone production to bail out Detroit. The immense fragility of the fabless model was violently exposed. The creation of the CHIPS and Science Act serves as a stark admission of failure from the United States government. The legislation injects $280 billion of funding into the domestic technology sector, with nearly $53 billion earmarked specifically for semiconductor manufacturing, research, and workforce training. It is a desperate emergency intervention to rebuild the exact factories that corporate America tore down decades prior. It is an incredibly expensive attempt to reverse 40 years of corporate financial optimization. America undeniably won the battle for the logic of the microchip. They control the code, they control the architectural blueprints, but they surrendered the ability to physically build the modern world. The relentless pursuit of capital efficiency decoupled the digital age from its physical origins. The most critical manufacturing infrastructure on the planet was handed to foreign foundries sitting on a geopolitically contested island. And the consequences of that separation now dictate the future of the entire global economy.